Assalamualaikum. Good morning, everyone. I hope you're doing very, very well. For a long time no see, and now we are going to have 1 hour class today. So, are these two QR codes working or not? Plus, it's working, eh? Is someone? All right. Okay. Thank you, Khairani. Okay, so it's working now. So maybe we just wait another 1 minute while I check in my computer. Oops. Section 415, right? And let me check on section 3. Section 3 is all working. Eh? All right. Okay. Section 3 is 21/28. Okay, that's very good. All right. Okay. So let us see what we can have today. All right. For our revision for our test 1, which is soon on Wednesday. This week, Wednesday. So I hope most of you already done your revisions. Basically, the topics already given in the e-learning. And then I believe what we want to do is to strengthen our knowledge, especially while we're doing previous past year questions. Okay. So just want to show you some of the question which is I've not shared with you just now in the morning. So let's see what we can have today. So this actually some of the questions, 3 past year questions, which are basically quite identical, all right? Quite identical, but not identical, but quite identical. Some of the question might be quite similar, okay? With your this one, okay? So let me record first. All right, and mostly some of the question will be asked also in the final exam. So yeah, so to be good, so we need to do, okay? So we have only 1 hour today, and then the next meeting on Thursday, which is after our test 1. So let's we do lah, okay? All right. Okay, so you might able to see some of the question will be like this. The question you can see this is from chapter 1. So given to you this kind of insulations, which is coming from through 2 different insulation materials. So we have the first layer. So let me get my pointer. So the first layer is a paper. So let's see the question is, you can see this transformer winding, okay, which is drawn like this, a plate, okay, just a model of plate. But the real transformer winding is a coil, okay, right? So make it easy, then we just make it a lump of coil in this kind of shape, okay, with the transformer winding. And now you can see the outer electrode is a transformer tank, and then between the winding and transformer tank are actually insulated with this paper and also mineral oil, okay? And you might see that this kind of paper, it has its own thickness. Given the thickness of paper insulation is 2 millimeters, and the thickness, I mean the gap distance is actually around 50 millimeters. Okay, all right. So 2 versus 50 millimeters, and then you got the total is 52 millimeters. And then both of the material, they have their own different relative permittivity, with the epsilon R represent the relative permittivity for the paper, and epsilon R2 represent relative permittivity for mineral oil. 4.4 for the paper and 3.0 for the mineral oils. So as what we know that we already learned in chapter 1, when we have different relative permittivity, we can have electric field displacements. Okay, so electric field become non-uniform on the interface between these two different papers because they have two different relative permittivity. So it's like a light that might be refracted. Okay, and then on the surface of these two papers, we have what we call as tangential electric fields. So this kind of tangential electric field is very, very dangerous. So we can increase the electric fields, and the electric field become nonlinear, especially on the interface. Okay, so based on this question, it's given to you, this transformer winding is energized at 275 kV RMS, and you are required to calculate the electric fields. Okay, all right. So if you still remember, so let me stop sharing. And then I want to share our slides. Okay, share. Oops, sorry. If you still remember, we have these slides, this multi-layer. Yep, yeah. Okay. So we have these layers with epsilon 1 represent material 1, epsilon 2 represent material 2. We have two different materials, and this is represent as a multi-layer. Okay, so every layer, it has its own electric field strengths, with E1 represent electric field strength for material 1, and E2 represent electric strength for material 2. And then these two layers also represented by two different voltages, V1 and V2, and then the total voltage, because they are considered in series, so they have two different two different voltages, V1 and V2, and then sum up become a total voltage, where the total voltage is the voltage applied at these electrodes. So for the voltage that we have in the question is 275 kV. And then by using this formula, so this formula is actually derived from this formula, V equal to V1 plus V2. And then with the different epsilon R, okay? And then finally we have E1 with these equations, okay? And then D2 should be multiplied with the fraction of epsilon 1 and epsilon 2. And then you might see that it has either increase or decrease. So it might depend on epsilon R1 and epsilon R2. Is epsilon R1 is more than epsilon R2? So you might see that the increase of denominator, and then E1 might be reduced. Okay, all right, yeah. So basically we learned from the previous case of, sorry, but I cannot go up. Yep, a little bit slow. Yeah, for the case of cavities, because cavity is air, it has lower epsilon. So you might see that this voltage will increase, sorry, electric field will increase in air compared to the surrounding insulations, where the epsilon R is more than epsilon R of the air. Okay, so then you might see that when epsilon R is reduced or decreased, then the voltage, the electric field will increase. All right, so you might need to use this formula to answer the questions. So let's go back to the questions. All right. So we need to use the formulas where, oh, sorry. So this is the answer. So let me get my pen. Yeah. Okay. So I need that the E1, which is the paper, E of the paper. So is equal to the voltage divided by D1 plus D2 epsilon R1 over epsilon R2. Okay. And then E of mineral oil, which is I consider as E2 or E of oil, is equal to E of the paper. And then epsilon R1 over epsilon R2. Okay, all right. So you might know we might see that D1 is 2 millimeters, D2 is 50 millimeters, epsilon R1 is 4.4, epsilon R2 is 3.0. Okay, all right. So then represent this in kV per millimeters because the voltage is in kV, and epsilon R, which is no unit, and D is already in millimeters. So you must see that your electric field is in kV per millimeters. Okay, all right. So by understanding the values, that you get here and you get here, then you must see that which electric field is higher. Okay, right? Yeah. So let's see the answers. So we might get the E of the paper is 3.65 kV per millimeters, and E of the oil is 5.35 kV per millimeters. Okay, so then you might see that the oil dielectrics with lower permittivity is stressed at higher electric fields. Okay, so this is the field strength that actually will be exerted. It's like a force will be exerted on the electric field. It's like a stress. So you might see that on oil, because it has lower permittivity, 3.0, compared to paper with 4.4 permittivities, then the oil is stressed at higher electric fields, okay, because of it has lower permittivity. Okay, yeah, so when I see that electric field is displaced into the material with lower permittivity. Okay, all right, yeah. So because of paper is 4.4 permittivity, then you might see that this is only 3.6 compared to 4.3, okay, of the electric fields of the oil. So more stress on the oil compared to the papers. All right, okay, so this is some of the questions that actually been asked on last semester. All right, okay, so this kind of question is chapter 2. So it's about Townsend mechanism gas breakdown according to the Townsend. So for the Townsend, we have first ionizations and we have second ionizations. The second ionization is through feedback process, which is due to the ion drift. Okay, and then the first ionization coefficient is due to the collision ionizations. Okay, yeah, so you might need to know that you need to have the experiment through the experiments. Yeah, because it's required to use diagrams. You might need to plot the diagrams, and then you might need to plot the IV characteristics. Okay, all right. So the experiment is using uniform electrodes where a small gap D, and then in a gas vessels. Okay, And then you need to also consider the avalanche. And then this is, of course, where we'll be ionizing the atoms and then release ion, okay, positive ion, all right? Yeah, sorry, release electron and then the atoms become positive ions. So you might need to discuss this in these Townsend mechanisms, right, with the ionization process. And then you need to draw a diagrams with the electrodes in the gas vessels, yeah, with small d, where you apply a small voltage, right? Yeah, and then a small current will flow, and then this will cause some ionizations. Electron will grow up, and then it will produce positive atoms. Okay, and then what we are going to see that from the IV catalysis. Okay, so when voltage is increased, and there you might see that some currents, polarization current will go up, and then because of non-sustaining discharge, so the current will remain constant. So this is called saturation currents, where there is no more voltage is increased. I mean, even voltage is increased to a certain level, but it cannot produce more electrons. And then the currents that flow in this circuit will remain at the saturation level. But then when voltage is increased and then it increase kinetic energy, then you must start to see that ionizations, and then it may produce alpha, which is considered as number of electron for ionization collisions. Okay, so these two of diagram you should explain so that you are able to, answer or describe briefly the Townsend mechanisms. You should have some keywords, ionization collisions, right? And if you want to consider feedback as well, it's fine because it's also considered as a second ionization process. And you need also to consider the multiplication of electrons, and then it may produce what we call have avalanche. Okay, correct. So this is some answers. You might see that here. Ionization process in which electrons, get my pointer here. So when electron is removed from the atom and then leaving atoms with the positive ions. So, and then for a small gap distance and also low pressure, okay, I forget to mention about low pressure. So the voltage difference between electrode will produce electric fields because we apply a voltage here. So it might produce V over D, we might produce electric fields, and then it may produce some kinetic energy that push the electron to move away from the cathodes, and then it travels because it's quite mobile. It travels from from cathode to the anodes, and then during traveling, it will collide with any of neutral atoms. So if the collision is inelastic and due to high energy of the electrons, because you got some energies is coming, either is coming from the electric fields, or it's also coming from the photoionization of the ultraviolet lights, and then it may release electrons and then really remain, leaving the atoms with the positive ions. Okay, and then after the number of electrons is quite high enough, and then it may produce the electron avalanche, and then it may produce higher currents, and then it can produce what we call as self-sustaining discharge, and then the currents going very high in terms of the exponential values. Right? So you might have another parameters here that is called as coefficient alpha in order to consider all the keywords. All right, okay, so that is for question on chapter 2. All right, okay, so this is on FDM. So FDM also will be asked in test 1 as well. And then you might see that basically FDM, you got a diagram like here, and then with a certain number of grid here, okay? So where we need to find every potential on every grid here. So according to the number, ascending numbers. So starting from 1, 2, 3 until the last one here is called a 16 here, sorry. Okay. So please read the question carefully. We have here a ceramic container is used for determining oil breakdown voltage according to this standard, IEC 615 standards. So basically, the gap is 2.5 millimeters if we consider this IC standard. We have ball bearing electrode where the voltage is applied. Okay. So you might see that the container comprises stainless steel ball electrode which are energized at 60 kV. So it means that both of the electrodes are energized at 60 kV. So here is 60 kV and here also 60 kV. So the container is then filled with the transformer oil. So inside here we have the transformer oil to prevent a surface flashover. So which covered up to 80% of the volumes or the total volume of the container. Okay, you must see another 20% over here, which is filled with the air mediums. So by using finite difference method, FDN, compute the potential at point, the grid 1, 1, 4, 6, 9, and 12. Okay, as shown in figure. And then we just limit the calculation to a single iteration only. All right, okay. So as we know, if air medium, so this point, this point, this, and this point will remain 0. Meanwhile, at this point, this point, this point represent the metal steel electrode, ball electrode. So this will be a 60 kV. Same goes to here, 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 and here will also be 60 kV, right? And then ceramic container is what they call it as insulation. So for the insulation, we consider the initial voltage is actually equal to 0 volt. So here will be 0, here will be 0, here will be 0, here will be 0. But how about here? Because here is still considered as all mediums. So all mediums, so we consider the voltage here will be 0, and the voltage here also will be 0. So we have 0 here, 0, 0, 0, 0, and 0 here as well. Okay, so let's see the answer. All right. So for the first V1 here, so it should be 60 plus 0 plus 0 here, and so 0 here. So it will be 60 divided by 4. Okay, yeah. Now you can see you got a 15 kV. And also V2, okay, V2 will be V1 plus 0 plus 0 plus 0 here. So it will be 15, V1 is 15 divided by 4. Okay, so you just continue one by one until you got the 12th one. Okay, so it's just a single iteration only. All right, so you just consider, okay, don't make any mistakes. So basically for insulation, the voltage will be 0. So air, oil is considered as insulation because it cannot conduct any voltage. And then be careful here, right? So here also will be 0, right? But because of this question, it's just up to 12. So this part will not be used. But if you consider, let's say you need to find 13 here. So you might need to know the voltage at this grid. So because the voltage at this grid is actually voltage at the inside the oil medium. So we consider this will be 0 volt. Okay. So this kind of question Yeah, you are going to meet this kind of question on Wednesday. Okay, so don't worry, I will share with you the slides after the class. Right? Okay, let's see the second set of the question. So this is 2023, 2024. This is about maybe 1 year ago. Okay. All right. So we are going to have this kind of questions. All right. So if you refer to slides, we can have some different type of field grading. So field grading technique is used to control the electric fields so that the electric field will not focus on one point, which is not localized at one point. And then if you local at one point, then you can increase the electric fields. So if electric field is over the down strength or dielectric strengths of that kind of materials, so then it can cause, it can give some energies to electrons, yeah, to travels, and then it can cause ionizations. Okay, but let's say for the case of solid insulation, it can cause thermal runaway, and then finally it can cause a breakdown of the solid insulations. Okay, so that is one that we don't want. Okay, but for this kind of question, you are required to provide one electric stress control technique, especially used for the cable joint and also the bushing. Okay, right? So I mean to say they are not the same technique, right? So basically we have two kind of techniques for cable joint. Basically we are using geometrical field grading. So if you still remember that we have sort of conductive deflector. Okay, so this kind of deflector produce some what we call as a Faraday cage, and then with a certain profile, curve profile, and then it can linearize the electric field, then electric field not focus at one point. Okay, and then another thing that we can also use as what we use is usually using semiconductive tape. So semiconductive tape, what we are going to see here, the kind of field grading is called refractive field grading, because semiconductive tape basically it has material with higher permittivity, so that it can refract the electric field, then electric field not focus at one point. Okay, so we just need to mention what kind of technique is used, and then we don't need to draw the diagram. Okay, but basically for the bushing, we are basically using a capacitive layer. So this kind of capacitive layer is called capacitive field grading, and then basically the voltage will be distributed over layers, every layers. Okay, and then the higher potential will be basically distributed away from the point that have higher permittivity, and then we are not so, I mean the electric field is not so stressed at one position only. Okay, so if you mention here capacitive field grading with some capacitive layer, right? So if you still remember, we have sorry, we have a layers. Okay, so we have different layers, right? So this is the bushing. Okay, so this is a transformer tank, right? So these are the bushing, the conductor of the bushing, right? So we have this capacitive layer, capacitive layer. So every capacitive layer, it had a capacitance. So this capacitance will behave as a voltage divider, and then it will distribute the voltage, because the higher voltage at this point, so this is the higher voltage, and then when the voltage at this point, it will reduce a lot. Okay, so according to this equation, E equal to V over D, so when your voltage drop, then your electric field also will drop. Okay, Yeah, so they make it this kind of capacitance layer, C layer, and it will distribute the voltage over it. All right, okay. And then this is another interesting question. All right. So if you read the question carefully, you must see that this, as a design engineers, you are required to determine an optimum design of the coaxial type conductor with inner and outer diameter. So you sort of you have coaxials, okay, all right. So where you have here diameter 1, inner diameters, and you have D2, the outer diameters. All right. And then as we know that electric field at the surface of the inner conductors is the maximum that we can see, isn't it? Right. And then the electric field basically will be distributed, yeah, from this is electric fields. Okay, so the maximum electric field is actually at the surface of the inner electrode, according to the skin effect. And then the only thing, because between these two electrodes, D1 and D2, okay, inner and outer electrodes. So in between we have the insulations. Okay, so insulations, different insulation, it has different breakdown strength. Okay, so given here, you might see that we have three different breakdown strengths. I mean, three different materials, insulation materials. So either air, which is gas, liquid, yeah, insulating oil, and then we have solid insulation. So different insulation materials, they have different breakdown strength. So if the breakdown strength over their strength, breakdown strength is the electric fields over their breakdown strength, then this insulating material may fail. Okay. And then we have also electric fields, relative permittivities. Given here, 1 for air, 2.2 for oil, and also for polyethylene, for liquid and solid insulations. Okay. As a design engineers, according to your calculations, right? According to the applied voltage here, 10 kV, 100 kV, and 1 megavolts, then you should design a suitable thickness. Okay. So that the electric bill may not exceed this value. Okay. If you consider air as your solid insulation, so you fill this gap, these two gap with air, then you might need to know what is the distance between the inner and outer electrodes. Okay, yeah, so that you can apply 10 kV at this electrode. Okay, at these electrodes, the inner electrode, and then there is no breakdown may happens. Okay, yeah. So how breakdown can happen? So if the electric field exceeds this value for air or for oil, okay, or for polyethylene, yeah, then you may need to consider the gap distance. Okay. All right. So this is the value that you need to calculate lah. The optimum inner diameter D1 and also outer diameter D2. So that the maximum phase strength is minimal. Okay, according to the given peak voltage. So let's say you apply 10 kV. So then you need to know how much the gap distance between the inner and the outer electrodes. Then you might need to consider this kind of considerations. So the minimal phase strength is chosen to be equal 0.67 EBD. So this is the EBD. So as the safety gap, the electric fields cannot be more than 67% of this. Okay, yeah. So we need to say, yeah, 30 kV per centimeter should be multiplied by 0.67 here. Okay, so what formula that we need to use? So we learned already. So we need to use this formula. So when you use this formula, we are going to get our minimum electric field ever. Okay, so this is the optimization technique that we use. And then this is the inner radius R2. Sorry, the outer radius R2. Then we need to convert it into diameters. Okay. Yeah, so because we know that R is equal to D over 2. Okay. So then this formula will be E1 min EV over D over 2. Right. So then you got 2 EV over D, D2. Right. Yeah. And then your E min, because E min cannot be more than 0.67 E of the breakdown. So it should be 0.67 E of the breakdown. Okay, so we need to use this formula in order to calculate. So what is the voltage? So these are the voltage that we apply, okay, according to the question here. 10 kV for the first condition, 100 kV second condition, and 1 megawatt, okay, for the third conditions. All right. So firstly, we choose air, okay, because we want to fill our coaxial conductors here, okay. So with air, so the distance, I mean the insulation between this gap D2 and D1 electrodes, we put air. So as we know that the breakdown strength of the air is smaller compared to the oil and polyethylene, then according to these equations, then we need to know what is a D2. Okay, yeah. So just now we have these equations, right? So 2 epsilon is equal to 2 point something there, just using calculator. So the voltage is the applied voltage that we use, 10 kV, 100 kV, and 1 megawatt. And then we need to calculate this D2, and then it will be interchanged with this 0.67 go down and D2 go up. And then we are using this formula. Okay, all right. So 10 kV, 30 kV per millimeters for the breakdown strength of the air. And then if we apply 10 kV, you must see that the D2 is equal to 2.7 centimeters. But how we want to find diameter for D1? We are still using this formula. Okay, so R1, okay, is equal to radius for we just multiply by 2 here. Okay, all right. Yeah, so we got 2 R2 divided by epsilon. So now it's equal to 1 centimeter when yeah, R2 or D2 here is equal to 2.7 centimeters. Okay, so it will be D2 over epsilon. Then you got 1 centimeter here. But when voltage is increased, then you must see that we need bigger gap between inner and outer electrodes. So the gap distance, the clearance is 10 times higher because the voltage is also 10 times. And when the voltage become 1000 kV, okay, 1000 kV, then it's become, the gap distance will become 2.7 meter. So you must see that the coaxial become very big in terms of size, okay. And then the same thing for the oil. So what values that we need to change? The breakdown strength of the oil is 150 kV per centimeters. So the rest will be the same. And then when voltage is going up, now you might see that the distance going 10 times and also 100 times. Okay, but if you compare between the air and also the oil, then you got a more compact systems, I mean the coaxial conductors. So the gap become smaller. But if you are using solid insulation, because the breakdown strength is 3 times higher than the oil, then you must see that it becomes smaller systems. Okay, so even when the voltage is going high, so it becomes smaller systems. Okay, So then we need to discuss our results. So as the result, the finding shows that the application of electrically strong insulating materials, so where the insulation material has stronger or higher let-down strength, then we can have a more compact design, okay, in comparison to air, okay. So you must see that if you are using polyethylene, our coaxial electrodes, D1 and D2, their gap distance is just become around, they are 80 centimeters, okay, around that. But this D2 is actually the diameters of the electrodes, okay, all right. Okay, I have another maybe around 50 minutes. I believe we can finish, all right, on time. Okay, so all right, so this is another questions. This is also quite important. So we must see that this is 500 kV dimension line, and this part is 100 kV, and on the right side is also 50, sorry, also 100 kV as well. But in the middle here, yeah, you might see that this is 50 kV in the middles. Okay, all right, yeah. So be careful. So especially when you want to find here, this is number 8. Okay, number 8, right? Sometimes you need to find here maybe 10, this is 11. So if you want to find this 11, so you don't need to calculate again because this is already energized at 50 kV. All right, yeah. So be careful, right? So you, because at this point, let's say this is number 10, this is number 11. You want to find V11, so you don't need to find. Okay, you don't need to put V10 plus V8, okay, plus here V12 plus here 0, right? Sorry, plus V12 plus 0 kV divided by 4. Okay, so you don't need to do this because this pole, you must see that this grid is already located at on the poles. Okay, and the pole is already energized at 50 kV. So you must just write the answer 50 kV. Okay, yeah. So be careful, right? Sometimes they ask you to search, and then yeah, sometimes because of spelling mistake, because you already understand, okay, because this is grid, then you need to follow this formula. Okay, but don't do that. Yeah, because the pole is already energized at 50 kV, you just straight away put V11 is 50 kV. Okay, all right, yeah. So this kind of question, because it is stopped at V9, so you don't need to find V10 or V11 or V12. Okay, all right. So let's move forward. Yeah, so this is very important. Okay, as you go through my videos, recording videos, I mean last week, because we have a synchronous class. So if you go through my videos, you might see that we have two types of gases for these Paschen's laws questions. So the first is we have air, and the second we have gas. Okay. So for air, you must, every pressure given, okay, you must do pressure corrections. Okay, you must correct the pressure. We call corrected pressure. And then every pressure given, you must divide by 1013. And then the temperature also you must correct. Okay, 273 273 plus 20 degree. And then the bottom is you plus the temperature given. Okay, yeah. I mean the measured temperatures. Measured temperatures. This is also measured pressure. Okay, so this is for air. Right, this is for air. For air, you must correct the pressure by dividing 1013. Okay, so if the pressure is given to you in millibar, okay, if it's given to you in ATM, you should divide by 1.013. Okay. If the pressure given you in torr, so you must divide by 760 here. Okay. All right. Yeah. So basically, we are given in bar, millibar. So that's why you should divide by 1013. Okay, 1013, 1013. So if given in ATM, you should divide by 1.013. Okay, if you given in torr, you divide by 760. Okay, this is only for air. Okay, yeah, you must read the question carefully. But if you read this question, this is actually gas. Okay, not air. So if gas, so P corrected. So P measured, okay, you just multiply by 273 plus 20 degrees, 273 plus temperature measured. So basically temperature measured will be given here, okay, right? And then pressure measured also will be given here, okay? So for the gas, you don't need to divide by the pressure, okay, 1013 or 1.013 or 760, okay? Yeah, so that is the main point now, right? So you must need to read the question carefully. So this is very careful. So basically for passion curve, we have passion mean here, we have at the lower and higher P and D, right? So this is the breakdown voltage, right? P is the pressure, D is the gap distance, because basically Paschen's laws, we are using uniform electric fields, okay, with the gap, and we have gas inside here with the atoms, right? And this is will be controlled by pressure. Pressure will control gas density. What does it mean by gas density? So the gas density is proportional with the atoms, right? Gas atoms. So if more pressure, so you have more gas atoms. Okay, so this is what we call as gas densities. And then according to these formulas, right? So these formulas is derived by gas breakdown criteria. Then we must see that we have here pressure corrected here and distance, pressure corrected and also distance here, D1, 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 and you got a V as 1, okay? And then we need to find A and B constants. Okay, basically two parameters will be given so that you have two simultaneous equations because you have two unknown parameter here, A and B. Okay, so basically we need to find A and B, right? And then the next question, you need, because you already have A and B calculated from the first questions, you have a complete equations. Then if you have a distance D and also you have pressure P, then you can calculate the breakdown voltage. Okay, all right, yeah. So basically, yeah, we need to follow lah. Okay, all right. All right, okay. So let's say here, yeah. But now you must see that for the second question, it's asked you to correct to the standard temperature of 22. Yeah, so here will be, here, so yeah, it should be 22 here lah. Okay, T measure, it should be 22. Oh, this question is not complete. So let me check. Oh yeah, okay. So actually it's not corrected. Actually, actually it's measured. And it's measured, all right? Yeah, it's not corrected, it's measured. Basically, we corrected at 20 degrees C, or sometimes it depends on the question. Okay, sometimes if the question asks you to correct at 25, so then this will be 25 here. Okay, depend on the questions. Okay, but in the table, this and this, all these are actually measured. Okay, all right. So the firstly, you need to calculate A and B because this is gas. Okay, so you might see that the temperature measured is 23. So 273 plus 23 will become 296. 273 plus 20 degrees C, so it become 293. So the first table is pressure at 300. So when we do temperature correction, it become lower, 296.96. And distance become 2.1. So we always use in centimeter. Okay, please use centimeter. All right. Yeah, and then you have the V1. The first V1 is 45 here, 45 kV, right? So distance given the gap distance between two electrodes here is 2.1 centimeters. And then it resulted into the breakdown voltage 45 for the first condition. The second condition is breakdown 80 kV. And then the gap distance is longer, right? Compared to 2.1 there. Then it caused the breakdown voltage to become higher. So it become 80 kV. But the pressure increase, as we know, when the pressure increase, then the breakdown voltage also will go high. And then when we do the pressure correction, become 273 plus 20 degrees C in Kelvin, and 300, it become 270 plus 27, it becomes 300. Then you must see that the corrected pressure is going down 886 millibar. Okay, and then when you put the values in the equations, then you might see that you got these two equation, equation number 1 here and equation number 2 here. Then you just use simultaneous equation, right? Either you want to use determinant or just use calculator only to unknown parameters. Then basically the calculation will give you the values, this value and this value x and y from the calculation. So you don't need to use determinant or Z matrix. Just straight away using calculators, and then you got a complete equations where V is equal to 0.01415, sorry, 141415 P and D plus B 1.448 square root P and D. Okay, all right. Yeah, so you got the complete equations. But now the next question given to you, the pressure 150, temperature 25 degrees C, the gap distance D is 1.3, then you need to calculate the breakdown voltage. All right, you know D, okay, 1.2 centimeters. You know pressure, but pressure you must correct it first. 150 multiplied by 293 divided by 295, because this 295 is 273 plus 25 degree here, the measured temperatures. And then 293 is 273 plus 20 degrees, the corrected temperatures. Okay, right? And then you convert this into Kelvin, and then you might see that even 150 will reduce a bit to 148.98. Okay, right? So you substitute here, rho D here, rho D here, and this D3, this 3, don't forget to square root this, and then you might get the breakdown voltage is equal to 2.21.89 kV. Okay, so it might be, yeah, because the gap distance is 1.2, so it should be 1.2 centimeter here, so it should be reduced a lot, right? Cannot be more than 45 kV, because 45 is 2.1 centimeters. Because the distance is reduced, then we may expect the breakdown voltage also will be reduced. Or okay, all right. Just check your question, okay? Because this is actually logic. All right, I have some more. This is last questions. So last question is on on theories of past chance laws, right? So basically, you might see that we have name of few gases in the insulation medium such as SF6, right? Yeah. So this is can be one of the gas, all right? Sometimes also we use nitrogen gas. So none of the theories explaining breakdown in gas breakdown. What kind of theory? Tungsten theories, Siemens theories, ionization process, theories, right? So you might say that when we have, so we have multiplications of electrons, and then leaving the atoms become uh, positive ions. Okay, all right. So this is what we might say that the ionization process is ionize the gas. Okay, the gas atoms. So what are typical conditions governing the ionization mechanism in right? Typical conditions, we need to have the ionization collisions, right? And then when ionize the gas through the collisions, then we might have the multiplication of electron that is called avalanche. Okay, so Paschen's law is used to explain breakdown correction with the pressure and gap distance P and D. So based on Paschen's curve shown in this, K1 explain the increment of breakdown to the left. So to the left we have lower PD, to the right we have our P and D. Okay, so we have low pressure. So when we have low pressure, so we have lesser gas atoms, then we have less ionizations. So when we have less ionization, so we need to increase our voltage. So when we increase our voltage, then we have more kinetic energy, then it can cause breakdown. So that's why the voltage is higher, because we need to increase more voltage. Okay, so the same goes to when we have longer distance. So because we to the right we have longer distance. So when we have a longer distance, then what we have here, the electric fields become lower because E is equal to V over D. So when D is higher, then E will reduce. So what we need to do in order to cause the breakdown, right, to cause the ionizations, then we need to increase the voltage. All right. So they are the same. And also when the pressure increase, so the main three parts distance we going down, and then we have lower kinetic energy electrons. Okay. So that will cause uh, the energy for the electron to cause the nation to reduce. Then we need to increase the voltage so that electric field also will go high, and then it will somehow supply more kinetic energy to electrons to ionize the atoms. Okay, I believe most of the answers already mentioned in the slides, but this is I'll put some slide here so that you can see. Okay, and these are the answers. So please do more revision on the Paschen's law, because the theory question quite a lot of kind of the theory questions. All right. So yeah, so you may need also to use this, all right, for your understanding, and then so hopefully you understand what is the Paschen minimums. Okay. Yeah. So basically, we don't need to have higher pressure, right, or lower distance in order to have the minimum breakdowns. But the partial minimum is that even at the lower voltage, then it can cause breakdowns. Okay, and this is called as partial minimum. All right, okay, class. Thank you so much. It's already 11 o'clock. Right, so I stop now. All right, I know some of you have class. Okay, thank you so much. I think I will share my recording after the class and also the slide as well. Alright, okay. So if you have any question, just text me.